Welcome to the student tutorials for Unit 3, Term 2, Specialist Mathematics. Today we're doing areas, volumes, and arc lengths, and my name is Stephen Crouch. We'll be taking you through a few tutorial programs where we get to see what areas, volumes, and arc lengths are, as well as calculate a few things. In today's session, we'll be looking and reviewing at regions bounded by curves and the x-axis and the y-axis. We'll be also calculating areas of these regions using our CAS. We're also going to review solids that are formed by rotating regions about the x-axis or the y-axis. We're also going to look at volumes of these solids. We're also going to review arcs of curves and how to find the length of those. And we're finally going to look at strategies for using our CAS to solve exam-style questions. Okay, so just before we start, we're going to have a look at this quick multiple choice question over here. Okay, so we've got the arc length of y equals x minus 2 to the 3 over 2 for x between 2 and 6. So have a go at that question. I'll give you a few seconds to have a look at that, and then we'll get started right away. Okay, so the first bit of business, let's look at regions between curves and the x-axis. So if we have a curve y equals f of x, and we basically create a region between that curve, the x-axis and the lines x equals a and x equals b, we basically get an integral, which is a equals the integral from a to b of fx dx. Now you might notice I've put x equals a and x equals b over here. I've actually put that there just to make it crystal clear that when you're finding the area of a region between a curve and the x-axis, we need to use x values in our integrals, and that's further specified by the x being at the end over there. Okay, so it's just something to help jog a memory and to also make clear that we're integrating with respect to x. So this particular rule here, it really applies to the specific case where the entire region is above the x-axis that is over the interval a to b. There are other cases as well where we need to modify this rule, which I will take you through right now. Okay, so this is the basic idea that we have. So if you have the area bounded by f of x, the x-axis and the lines x equals a and x equals b, the area is just the integral from a to b of fx dx, as I stated before. All right, so this is the sort of foundation case that we have. Another case that we've got as well is if fx is always underneath the x-axis, at least over the interval a to b, then the area is pretty much the same thing, except we need to put a negative out the front of the integral. And the reason behind that is because when you find the area via this integration here, the answer will be negative. So you simply place a negative out the front of that to counteract the fact that the integral itself is negative. Okay, so the final case is if your function crosses the x-axis once or more times between the start and end points of the interval. So in this particular example here, we've got f of x that is above the x-axis between a and b, but between b and c, it's below the x-axis. So to find the area, you simply integrate the function between a and b, and that will give you that area as a positive area. And then you find the integral between b and c of f of x, which will give you a negative answer. So when you subtract this negative answer, it adds these two areas together. Okay, so that's just the basic theory behind the areas between regions and the x-axis. Let's look at our first exam-style question, where we get to basically try out this theory and get to see it in practice. Okay, so here's our question. Let's find the area between the curve fx equals 1 over root 9 minus x squared, the x-axis, the y-axis, and the line x equals 3 root 3 over 2. So first things first, what I might do is simply define the function over there, so that later when we get to graphing it and integrating it, it's easier to do that rather than typing this over and over again. Okay, so if you're wondering how I got this this line over here, I'll go through it again. It's basically f open bracket x close bracket, and to get the to get the defined symbol, so I'll just go f of x again, f of x, to get the, so to get the defined symbol, we simply go Control, and we press this template button over here. So pressing Control and that template button there basically is what we call the assign to command. So fx is assigned to, and let's type this out. So Control and divide 1, and then tab over to the bottom, and let's square root 9 minus x squared. All right, so now that we've got that over there, we've now basically now just gone and defined f of x in terms of x. All right, so let's go have a look at what this region looks like before we actually go and find its area. All right, so what we've got here is I've got just a blank axis of here, and I'm going to show you how do we construct this region. So this is our function fx. This is fx equals 1 over square root 9 minus x squared. Here is the line x equals 3 root 3 over 2, because that's the line stated in the question. So I've got that, and now what I've got is I've basically shaded in gray the region that is enclosed by fx, the line x equals 3 root 3 over 2, the x-axis, the y-axis, and this line over here. Okay, so we've got a whole bunch of bounds over here, and those bounds together make up the boundaries of the region. So that's the region right there. Now, when we eventually do calculate it, we'll get something like that. But of course, we want the exact value. So let's see how this works out. So what I'm going to do is I'm just going to start by performing an integral. And a nice handy shortcut for integrals is Shift plus. Okay, so I'm going to press Shift plus, and the two bounds of integration, the lower x value is 0. And then I'm going to press Tab to go to the upper bound, and going to put in the fraction there. So 3 square root 3 over 2, and then I'm going to go to the integrand box over here. So I've already defined the function, so I'm just going to go to var, and then f, and then basically put x over there, and then keep tabbing over until I get dx. Okay, so once that's done, I'm going to press enter, and I get pi over 3. So the answer to the question, what is the area between the curve f of x, the x-axis, y-axis, and the line x equals 3 root 3 over 2? The answer to that question is pi over 3 square units. So when you're writing out this as a textbook question or exam question, and you're writing out the answer, you have to put square units at the end of this, or units squared. It's up to you, but you must state some sort of units that this area corresponds to. Okay, so let's look at another different type of exam style question. This time we want the area between the curve, g of x equals x over root 1 plus x squared, the x-axis and the lines x equals negative root 3 and x equals positive root 3. Okay, so as I did before, I'm going to start by defining the function. I've already got the initial part there, so let's finish it off. So I've got that, and then x divided by square root, there we go, no? So x divided by square root of 1 plus x and then squared. Okay, there we go. So I have g of x defined as x over square root of 1 plus x squared. Okay, and now let's have a look at what this graph looks like. So here's another blank axis. So yeah, this is what the graph of y equals g of x looks like. X equals neg 3 is, of course, this vertical line on the left. And now the region enclosed by x equals negative root 3, the x-axis and g of x has an area of 1. Okay, however, it's showing as negative 1 over here because the integral from neg 3 to 0 of g of x will, of course, give us negative 1. We'll get to that later when we have a look at the calculator application. Okay, so our next line is, of course, x equals root 3, and we've now got an area of 1 for that. This is, of course, a symmetrical function, so that's why the areas are the same on both sides. Okay, so how we're going to go through this is let's have a look at our integration. So again, Shift plus, So Shift plus gives us our integral, and if you look back at this graph over here, we're going to integrate from 0 to root 3, and then we're going to subtract the integral from negative root 3 to 0, okay? Because we want to do the positive first, and then the negative area second. Okay, so we have negative, and then square root of 3, and then tab, and then we have 0. Okay, so that is actually the negative one, so let's put the negative there. And then we want var, we'll go down to g, and then x. Okay, so we've got g of x dx, and then we're going to add on the integral for the positive section. Right, so you have 0, tab, and then square root 3, and then tab over, and then again, let's go find g, and then put x in there, and there we go. Okay, so what we've now got is the integral from 0 to root 3 of gx. So this one was 1, as you saw on the graph before, and then this integral here was -1. So taking the negative of that will basically make it a +1. +1 plus 1 is, of course, equal to 2. So the answer to the question for the area between the curve and these different lines is basically 2 square units. All right, so the next part that we're going to look at is what about regions between two curves? So if you have two curves, y equals fx and y equals g of x, if you want to find the area of the region that's between these two curves, at least between x equals a and x equals b, you simply need to take the difference of the two functions, making sure that f of x is above g of x within the interval. If g of x is above f equals a, above f of x, then you simply swap the order of that. Okay, so this rule applies to the case where f of x is greater than gx for all x in the interval from a to b. Okay, and of course modifications happen for other cases. So here we go. Here is the simple example of what I was referring to before. If you have y equals f of x, which is this curve over here that's above the region, and we have y equals g of x, which is this curve below the region, the area enclosed by these two graphs is the integral from a to b of fx minus g of x dx. Now, if you have the two graphs intersecting at some point within the interval that we want to find the area of, then you have to perform separate integrations, and the order of each integral will depend on which function is above the region and which is below the region. So looking at this first region over here, we have f of x above. So y equals fx is the function that's above the region in the interval a to b, and g of x is, of course, below the region in a to b. So the integral here is from a to b of fx minus gx dx, just like it was before. Now, between b and c, you notice that g of x is now living above the region, and f of x is living below the region. Okay, so in that case, our second integral is going to be from b to c, but we now have g of x minus f of x. Okay, so just something to keep in mind. So therefore, it's always a good idea to look at the graph of a function before blindly integrating it to find the area. Okay, so here we are. Let's look at the area between the curves y equals 1 on 1 plus x squared, y equals 1 over x minus 1 squared, and the lines x equals 0 and x equals 1 on root 3. So before I go and define what f of x and g of x are, what we might do is just have a look at the graph. Let's have a look at the visual representation of the region we're talking about. So this red graph here is the truncus given by the equation y equals 1 over x minus 1 squared. And this blue graph here is the graph of the function y equals 1 over 1 plus x squared. And this green vertical line here is x equals 1 on root 3. So as you can see, between the within the interval given by 0 to 1 on root 3, we've got the truncus being above the this bell curve over here. Right, so what that means, what that suggests is that we probably should define f of x to be the truncus, which I will go ahead and do right now. So 1 over, and then bracket x minus, we have x minus 1, and then squared. Enter, and now let's define g of x. So g, I've got g here, bracket x, and let's now define that. Okay, so let's define that as 1 over 1 plus x squared. Okay, so there we are. We now have f of x and g of x both having been defined. Okay, so now we've got everything ready to go. Let's go and perform the calculation. All right, so here's where we're going to go. Shift plus, and let's integrate from 0 all the way to 1 over square root of 3. So there we go. That is, those are our bounds of integration. And we're simply going to take f of x minus g of x dx. And there we go. Okay, so we've basically got this, the sum of various different fractions over there. If you'd like to write that as a single fraction with a single denominator, then you're certainly welcome to go to Menu, then Algebra, Fraction Tools, and Common Denominator. So you can use a bit of algebra to help you with simplifying a couple of the outputs that you get. Okay, so this might be written as 3 plus 3 root 3 minus pi all over 6, or you can just write 1/6 multiplied by all of this in brackets. Okay, so the option is there for you to use, especially if the exam paper or assessment has the answer written in a particular form where it says find the area, giving your answer in the form so on and so forth. Okay, so there we go. There is our area, and this is what we've got going on over there. All right, so let's look at the next section. So the next section is let's find the region, the area of the region between a curve and the y-axis. Okay, so this one's a bit different, but the maths works very similar to what we had before. So if you have the curve y equals fx, and you have the y-axis and the lines y equals a and y equals b, so you notice how everything over here is now in terms of y. The area is given by the integral from y equals a to y equals b of the inverse of f of x with an argument of y integrated with respect to y. So this is the reason why I had x equals a and x equals b in the previous topics, because now when we integrate and we want an area between a function or a curve and the y-axis, we're now going to integrate from a lower y value to an upper y value. So you have to be very careful with these things over here. Okay, so as before, this rule actually only applies to the case where our region is in on the right-hand side, so in the first or fourth quadrant of the Cartesian axes. So if there are any other cases, you have to modify your integral accordingly. So here we go. So over here is basically a function. It's not really a function, it's a relation. And as you can see, we've got the region between the curve and the lines y equals a and y equals b. So one way to think about it is to basically rotate these axes in such a way that the y-axis is now on the horizontal axis and the x-axis is on the vertical axis. And then what happens is you've now got this region basically appearing as an x integral, okay, as we had before. It's just that we have x on the top and y on the side. In a similar fashion, if your region exists to the left of the y-axis, then when you swap the axes, the region now appears underneath the y-axis over here. So if this happens to be the case, if your region is to the left of the y-axis, then we normally put a negative in front of the integral when we're finding the area. Okay, so here we go. Here we have a function, y equals inverse sine of 2x, and we want the area between that curve, the y-axis, and the line y equals pi on 4. All right, so before we get started, let's just define this function here. So trig, inverse sine, and then simply 2x. All right, there we go. So I have fx defined as inverse sine of 2x. Now that that's done, we can then look at the graph. Okay, so here we go. So here is the graph of y equals inverse sine 2x. That red line there is the line y equals pi on 4. I've only drawn the line y equals pi on 4 between x equals 0 and x equals half, basically because that's the only part that we need at the moment. And then, of course, the region that we want is shaded over here in gray. Okay, so let's go ahead and find this area. All right, so first thing we need to do is we need to basically solve this equation for y. The easiest way to do that is menu 3.1, solve, and then we're simply going to put f of y is equal to x and solve for y. Okay, so what we now have is we have y equals half of sine x. And as you can see, it's only defined between negative pi and 2 and pi over 2. And the reason behind that is because the original inverse sine 2x function is defined between negative pi and 2 and positive pi on 2, or negative pi and 4 and positive pi and 4 in terms of the y values. Okay, so when you do the inverse, the domain and range will of course swap away like that. Okay, so there we are. This is y in terms of x. However, what we need to do is when we perform the integral, we need to do this in terms of y's. Okay, so let's see how we do that. So shift plus, and here's our integral. And we want the integral from the y-axis to the line y equals pi and 4. So looking at the graph again, the lowest y value is 0 because it starts at the origin. It goes all the way up to pi on 4. So those are our two bounds. So 0, and then tab, let's start up a fraction, and we have pi, and then on the bottom we have 4. Okay, and then over here, what's the function we've got? We've basically got half sine of y. Okay, so I'm going to put a fraction, half, and then trig, sine of y, and then dy. There we go. Okay, so this right here is the integral that basically gives us the area of the region between y equals inverse sine 2x, the y-axis, and the line y equals pi on 4. And that's how you get the answer of 2 minus root 2 all over 4. Okay, so there we go. That is how that question gets done. All right, so moving on to the next section. We've now finished up with areas. Now let's look at solids of revolution. Okay, so one of the ways to revolve a region about an axis is to do it about the x-axis. So if you take a region that's enclosed by the curve y equals fx, the x-axis and the lines x equals a and x equals b, you take that region and you rotate that region about the x-axis. The volume of that region is given by this integral. So it's pi times the integral from x equals a to x equals b of the square of the function with respect to x. Okay, so this is one of the applications of integration that we learn about in specialist maths. So this is what one of these solids typically looks like. This blue curve here is a parabola, and this green sort of solid over there is the sort of solid that you get when you take that parabola and rotate it about the x-axis. So you get some really interesting shapes and curves and objects with this topic over here, which makes it ever the more exciting to study. Okay, so let's have a look at our next exam style question where we get to try out this theory. So we have the curve y equals 1 over x times square root of 2x plus 4. And we want to rotate the region between that curve, x equals half and x equals 3 over 2. And we want to rotate that about the x-axis to form a solid of revolution. Okay, so before we get started, as always, let's define this. So here's our fraction, 1 over x multiplied by square root of 2x plus 4. Okay, so there it is defined. Now, before we get launched into doing the mathematics, let's actually have a look at a visual look at what's going on over here. So this is y equals fx. This is our curve. Here's x equals half and x equals 3 over 2. So this gray region over here basically represents the region that is going to be rotated about the x-axis to form the solid of revolution. And you might be asking, what does that solid of revolution look like? Well, it actually looks like this. Okay, so this shape that you see in front of you is in fact the look of the solid after you revolve that region about the x-axis. So here, as you can see, this is the x-axis, and this shape of here represents the solid that was formed by that rotation. Okay, so that's what it looks like. So now let's get into the maths of how this works out. All right, so I'm just going to apply the formula as it was stated, and I'm going to go shift plus, and then we're going to choose half for the lower bound, and then 3 over 2 for the upper bound. Okay, there's no need to use fraction notation for those ones over there. Just trying to keep it in the one line over here. And all we're going to do is open a bracket and go find f of x, and then we're going to square that and integrate that with respect to x. Now, when you look at the answer, you get a pretty complicated answer over here. What I might do is I might just copy this to a new page so you can see the entire calculation slightly better. All right, so let's go to a new calculator page, and there we go. Okay, so what we need to do is this is the integral, but before you say that as the final answer, you're going to multiply it by pi, and then you get this answer over here. Okay, so it looks like a pretty complicated answer over here. There's a lot of logs floating around over there, and of course you can modify this in such a way that the 3 log E7 minus 3 log E15 is displayed as a single logarithm, if you prefer. Okay, so this is what the actual volume of it would be. If you could convert to an approximate answer, it's about 0.75 is the volume of that solid revolution. Of course, when you write the answer, unless the question specifies decimal places, you must leave your answer in exact form. And also don't forget to put cubic units or units cubed at the end. Okay, so that is how you basically revolve a region about the x-axis and get its volume. Okay, so of course the next stage would be to revolve a region about the y-axis and find the volume of the solid that was thus formed. Okay, so when you have a curve given by y equals fx, and then you've also got the y-axis, you've got the lines y equals a, and you've got the line y equals b, and you take that region and you rotate that about the y-axis, the formula used looks a bit different from the x-axis revolution formula. Now it is pi times the integral from a to b, but these a and b are actually y values of x squared dy. Now, what is x, you may be asking? Well, x is just the inverse of the function with y basically plugged in. Okay, so that's how that question works out. Now, in the majority of cases, what actually happens is the curves that you have already have x squared in there. So when you go and solve for x squared, you don't need to actually go and solve for x and then square it. You just perform algebra in such a way that you end up with x squared as the answer. And you'll see that in our next exam style question. Okay, so this is a sample again of what a solid of revolution about the y-axis looks like. So this is in fact y equals square root x. This is y equals square root x from the x-axis, as you can see. Now, if you rotate that about the y-axis, you get this really nice looking shape. It almost looks like a spinning top. Okay, so that's really, really nice over there. Okay, so here is our second last exam style question for today's tutorial. So we've got the curve defined by 4y squared equals 1 minus 1 over x squared. Okay, and we want the region bounded by this curve, the x-axis, the y-axis, and finally the line y equals a quarter. And we're going to rotate that about the y-axis, and let's see how that works out. All right, so this is the curve. So it almost looks like a sideways parabola. 4y squared equals 1 minus 1 over x squared. This red line here is the horizontal line given by y equals a quarter. So the region that is specified in the question is this gray region over here. So it's between the x-axis, the y-axis, the blue curve, which is our given relation, and we've also got the red line y equals a quarter. So that is what we have over there. So just pay attention that the two y values that we're going to use on our integral are y equals 0 and y equals a quarter because they represent the bounds. Okay, so before we get any further, let's have a look at what this visually looks like. There you go. So this is a sort of lower resolution version. Here's a bit of a higher resolution version. This right here is basically the outside of the solid that was formed. Okay, so this is, as you can see, here's x and here's y. So I've tried to basically put the angle in such a way that we've got a similar viewpoint to what our 2D was. Okay, so here's x and here's y. So if you rotate that function, or that curve rather, about the y-axis, the outside of that solid looks like that blue object over there, right? So again, pretty cool visuals over here that you get from solids of revolution. Okay, so let's head back to our calculator mode. All right, so what we might do is take this function, 4y squared equals 1 minus 1 on x squared, and let's solve that to get x squared by itself. So I'm going to simply type in 4y squared equals 1 minus 1 over x squared. So I'm just going to type this, and we're now going to apply algebra until we get x squared by itself. So I'm going to add 1 over x squared to both sides, okay? And then we're going to subtract 4y squared from both sides, and then we're going to invert both sides, so we finally get x squared equals -1 over 4y squared minus 1. And this is what we now put into our integral. So there's no reason to square root both sides and get x by itself. You simply leave it in this form and then perform the integral. Okay, so as I said before, the integral of the that represents the volume of the solid of revolution is pi multiplied by shift plus, which is the integral. Now our 0, our upper y value was 1/4, and x squared is this particular fraction of So I'll just write it as 1 over 1 minus 4y squared and integrate that with respect to y. Enter, and there we go. So we basically get pi on 4 times log E3, which is a really nice looking answer, and that is the exact form. So the answer to what is the volume of solid of revolution for the specific scenario is basically pi on 4 times log E3 cubic units. All right, so let's move on to our final section, which is now talking about the arc length. So if you take a curve y equals fx, and then you basically generate the arc from x equals a to x equals b, the arc length of that particular section is given by the integral from a to b. Now just remember, these a and b are x values. So the integral from a to b of the square root of the sum of 1 and the square of the derivative with respect to x. So you take the curve y equals fx, you differentiate the function, you square the derivative, you add 1 to it, you square root that, and then you integrate that finally between x equals a and x equals b. Okay, so this is just a quick picture that I put together that kind of demonstrates where this comes from. So we basically got a dy as horizontal derivatives, and a dx as dy as a vertical differential, dx as a horizontal differential, and dl, which is basically an infinitesimally small length of arc, is what's going on here. So from A to B, as you go along from A to B, this dl shows you will add up together to form the arc length. So the derivation is beyond the scope of the course, but it certainly is worthwhile and interesting to have a look at it. Okay, so now let's look at our very final question. Let's find the arc length of the curve y equals x minus 2 to the 3 over 2 between x equals 2 and x equals 6. Now this one was our warm-up question at the start. So now we get to see how to work out the question. Okay, so without further ado, let's go and define this function. So we have x minus 2, close bracket, to the power of 3 over 2. There we go. So we've now defined it. So let's now find a whole bunch of things over here. We need to find the derivative of this. And the easiest way to do that is I'm going to call it df as for derivative of f of x. And I'm going to define that as shift minus the derivative with respect to x of the function f of x. Okay, so that is now our derivative. So when we get to our integral for the arc length, we get to basically plug in df of x and take it from there. So here we go. So shift plus, and our x values are 2 and 6. Now let's create our integral. So square root of 1 plus open bracket var, so df x, close the appropriate brackets and squares. There you go. That's the square root of 1 plus dy dx squared with respect to x, and there we go. Okay, so this right here is the answer to the arc length of that particular curve. All right, so that is it for this session. And before we go, what I might do is just show you what that arc represents. So this is y equals f of x. It is just the function y equals x minus 2 to the power of 3 over 2. And here is the particular arc that we found the length of. So x equals 2 to x equals 6. This particular section of the curve right here is the exact length of what we just found. So if you place a string starting here, going along the curve and ending there, the exact length of that string would be 8 on 27 times 10 root 10 minus 1. Okay, that is it for this session. Thank you so much for joining us today. All the best with your studies, and I hope you can join us for the rest of the Term 2 tutorial sessions as well. Thanks, everyone, and good afternoon.